All right, so we learned about the definite integral. The definite integral being just a Riemann sums, adding up a bunch of rectangles, where we're looking at infinite number of rectangles. And so it's a way to take something that's a Riemann sum approximation, but when we look at the definite integral, when we let our n approach infinity so that our dx is infinitely small, where dx is my base width, we go from getting an approximated area to an exact area. So how do we use it? Well, earlier in this lesson, we were looking at the integral, or rather, we were looking at the area under the curve root 16 minus x squared. Um, so drawing that again from -4 to 4 and 4. And so what this definite integral is saying, and there should be a dx in there, what that definite integral is saying is find the area under the curve. Well, first of all, we could do this without using any calculus, because we know that this is a circle, and the area of a circle, it's half a circle, is pi r squared over 2. So the area, this is the top, the numerator is the area of a circle, and we're dividing it by 2 because it's only half a circle. So our area, we should expect it to be, pi times 4 squared over 2, which, if we put into our calculator to get an answer, an exact answer, or an approximated answer rather, pi times r squared over 2, we get 25.13. And that should feel pretty good to us, because if we go back to what we started class with, this is kind of messy, but we were looking at this area, and as n got really big, so as n got huge, we were approximating that area to be 25.1 something. And in fact, that's what we're getting, 25.1 something. But how would I do this using the calculator? Well, before I do this using the calculator, before I show you a new function, I just want to remind you that what we're doing is we're taking a little strip, and this is really important that you understand sort of conceptually what's going on. And this little strip has width dx, and it has height. Well, it has the height of this function, and that height is 16 minus x squared. And I'm adding up all of these rectangles. So there's an infinite number of rectangles, and I'm adding up all of these rectangles from when x equals -4 to x equals 4. And when I add up all of these rectangles with width dx and height 16 minus x squared, when I add up all of these rectangles, eventually what I'm going to do is approximate the area underneath that semicircle. Well, how do I do that using the calculator? What we do, um, first thing, get out your calculator, and you should do this along with me. Um, let's put the function into y1. Once you get that function into y1, second calc is like the mecca of not the mecca. It's the hugest place. It's the most critical place on earth as far as calculator functions are concerned. If you don't have a TI-83 or 84, I will show you outside of class how to do this. Your calculators can probably do this as well, but I'm talking in particular about the 83 and the 84. So if we go second calc, and we're going to go down to 7, because look, that looks like the integral of f of x dx. And we're going to press enter. So our lower limit, well, our lower limit is -4. That's our lower bound. So we're going to put -4. And our upper limit, that's 4. So we're going to press 4. And when I press enter, you're going to see the calculator shading in the area underneath the curve. And the calculator gives me the area is 25.13, which is exactly what we expected it to be. So, scrolling down, once you get to that function under calculate the integral sign, we just put in the lower limit and the upper limit, where the lower limit is coming from the bottom and the upper limit coming from the top. And when we do that, it shades in the region, reminding us that we're finding the area, and it will give us what that definite integral is. Pretty cool. All right, so let's look at a couple more examples. So we're gonna evaluate this definite integral in a number of different ways. Um, before we evaluate it, let's get a picture of what it looks like. So we've got the function 3 minus x. So we're gonna get something like that, and we're looking for this area where the red is gonna be positive area and the black is gonna be negative area. So we want to evaluate the following in three different ways. One, using our Riemann sum program, where n is 100, using a right bound. The second, we want to use the new integral function that we just learned. And then the third is to confirm that we can actually find this using geometry and what we know about triangles. So here we go. Finding it using the Riemann sum program. So whenever you're doing a Riemann sum program, first thing that you need to do is put the function into your y1. So we put in 3 minus x, and then we can quit out. And we want to do our program, so we go to program, press enter to execute, enter. And our left bound, well, our left bound is 0, so we put 0. And our right bound is 5. That comes from up here. And our x choice, well, we want to do a right bound, so our x choice should be 1. 1 stands for right bound. And the number we're asked to find when n is 100, so we're having 100 rectangles, which is a pretty good approximation. It's not as perfect as a definite integral, but it's close. And when we press enter, it's going to spit out for us a value. Now notice the calculator's thinking because it takes a while to compute all those values. So using our Riemann sum program, we get that the area underneath that is 2.375. Well, what if we wanted to use the integral function? Hopefully we're going to get something similar, but this is just good review of how to use the calculator, which is an important feature of this class. So I would highly encourage you to be doing this with me as I'm doing it. So I want to use the integral function. Make sure the function is still in my y1. It needs to be in there. And then I'm going to press second calc, and I'm going to go down to 7 and press enter. There's my graph, and I want a lower limit of 0 to an upper limit of 5, and it's going to shade in that area, and it spits out a more exact area of 2.5. Okay, so these two answers are pretty close. Our Riemann sum is an approximation. The integral function is pretty exact. The calculator does do a little bit of approximating. We're going to learn how to do this totally exact in the next couple days. But for now, those are two methods. And our last method is to use geometry. So on curves that on straight line curves or semicircles or anything that we can use geometry for, always know that that's totally acceptable. So what do I mean by that? We've got this line, and we're going to 5, and this is 3. So we've got two triangles going on. We've got this triangle here, which is height of 3, width of 3. So this area here would be 1/2 3 times 3, which is 9/2. And that's positive area because it's above the x-axis. And then we've got this other triangle down here. Well, from 3 to 5, it's got 2, and we go down 2. So this area here, which is a negative area, is going to be negative 1/2 base times height, which is negative 4/2. So the total area then would be the sum of those two areas. The area represented, understanding that anything under the x-axis is negative, would be 9/2 plus negative 4/2, and adding those up, we get that it equals 5/2, or 2.5. And this should be nice to see because it's exactly the answer that we got using our integration function. Okay, so we've looked at one way of using the calculator, and I want to add a second method, just so that you have a couple different options. So let's say I'm trying to find this definite integral. So reminder, what is a definite integral? You know, 1 over x is a graph that looks like this, and I'm looking from 2 to 5. So what I'm doing in finding this definite integral is I'm making a bunch of strips, and each strip has a width of dx and a height of 1 over x. So 1 over x dx, that's the little area. And we could call that dA. D standing for, really small area. But what I'm going to do is I'm going to add an infinite number of those strips, which will then approximate the area completely for me. So the method that you know so far is to use that second calc feature. So just a reminder of that, you could go, into your y1, enter your new function, and go to second calc, and we want to do the definite integral from a lower limit. Well, our lower limit is 2. And my upper limit is 5, and that comes from the limits of my integration. And it's not as clearly darkened because it's very close, but down here you can see it's dark, and that area is 0.916. So using the second calc feature, we get an approximation of the area of 0.916. Well, there's one other feature which I think is actually a little bit quicker, and the way that you do that, if you get your calculator out again, and you get the function 1 over x into your y equals. Now, instead of using the second calc feature, this next feature is really good if you want to take multiple integrals and you don't want to keep having to do second calc, second calc, second calc. So what you do is if you press math here, so you should have a screen that looks like this. And then we're going to go down, scroll down until you see fn int. So function integration. That's what that stands for, function integration. And then press enter. Ooh, I made a mistake. Sorry about that. In y1, after you get 1 over x, once you put your function in, you have to quit out. So quit out. Then press math. Go down to function integral. And you should see this function integral. And what we want to do is we want to tell the function that we want to integrate what's in y1. So we have to put y1. So if you press vars, y vars, function y1. So now we're integrating, that's this sign, we're integrating the function y1, and the variable that's being integrated is x. And so for single variable calculus, which you'll be doing this year, it's always going to be comma x. And then you put the limits of your integration. So we're integrating from 2 to 5. We're integrating from 2 to 5, so we put comma 2, comma 5, press enter, and once again we get the same answer, 0.916, the area under this curve from 2 to 5. It's a different method. You may like it, you may not, but both exist, and you should be comfortable or at least understand how to use both. There's just a little bit more to do in this lesson, so that we're going to have one more video, but the next video is pretty short. Thank you.